What's up, everyone? Today we're going to be spending a lot of time talking about polynomials. In a previous video, we've covered some important groundwork, things like what a proof system is, what it means for something to be zero knowledge, and most importantly, what a zkSNARK actually is. If that definition isn't fresh in your mind, I'd recommend checking out that video first and then coming back here. It'll also help a lot if you're familiar with finite fields, at least at a basic level. As it turns out, polynomials play a huge role in how zkSNARKs are constructed. So in this video, we're going to focus on the polynomial tools and ideas that show up again and again in zkSNARKs. In this video, we'll focus on univariate polynomials, polynomials with a single variable. But many of the ideas also extend to multivariate polynomials, which we may explore in a later video. This video will be slightly longer, as we'll be covering a wide range of topics, each of which is essential to understanding zkSNARKs. But I hope you'll stick around for all of it. The good news is that the prerequisites are pretty light. As long as you know what a polynomial is and you're familiar with the definition of a zkSNARK, you're all set for this video. Alright, let's get started. For those of you who like a sneak preview, let me start with a quick roadmap for how we're going to build up to a zkSNARK. The first major ingredient is polynomials. That's what we're focusing on today. Once we're comfortable with those, we'll introduce two key tools, PIOPs, which stand for Polynomial Interactive Oracle Proofs, and PCSs, or Polynomial Commitment Schemes. We're going to need both of these, and it's no accident that they each start with the word polynomial. After that, we'll see how a PIOP and a PCS can be combined to give us an interactive public coin proof for arbitrary computations. From there, we'll apply the Fiat-Shamir transform that we learned about to remove interaction and turn that proof into a snark. Finally, we'll add zero knowledge on top, transforming the snark into a zkSNARK. But before we get too far ahead of ourselves, let's take a step back and ask a more basic question. Why are polynomials so important in the first place? Polynomials have a lot of cool properties, but one of my favorites is their ability to aggregate or collect a whole bunch of information into a single mathematical object. Let me show you what I mean by that. Let's say I have four equations. I have 2 plus 1 equals 3, 4 plus 4 equals 8, 14 plus 19 equals 33, 38 plus 58 equals 96. At a first glance, these look like four completely separate equations. But here's the neat part. We can actually condense all four equations into a single polynomial relationship. To do that, we create three polynomials, one for each column of the equations, and call them a of x, b of x, and c of x. The first step is to assign each equation a unique input value. Let's label the rows with the x values 0, 1, 2, and 3. The first equation corresponds to x equals 0, the second to x equals 1, and so on. The exact numbers don't matter for now. The only requirement is that each row has a distinct x value. Using 0, 1, 2, and 3 just keeps things simple. At this point, we've only labeled the rows. We haven't built any polynomials yet. Now let's build our polynomials. The goal is to turn each column into a polynomial, meaning we define a of x, b of x, and c of x, so that evaluating them at a row's x value gives the values from the original equations from that row. That sounds a bit abstract, so let's go through it one step at a time. For the first row, what we're calling row 0, we set a of 0 equals 2, b of 0 equals 1, and c of 0 equals 3. For the second row, which is row 1, we set a of 1 equals 4, b of 1 equals 4, and c of 1 equals 8. And we keep going like this for the remaining rows, assigning values so that evaluating each polynomial at a given row number gives us the entries from that row. At this point, you might wonder whether such polynomials even exist, and if they do, whether they're unique. Going back to the fundamentals of algebra, there's a key fact that tells us that if you specify the values of a polynomial at n distinct x values, then there is exactly one polynomial of degree at most n minus 1 that fits those points. Now, how to find this polynomial? We can do it using something called Lagrange interpolation. We won't go into the details here since there are plenty of resources online if you want to explore the details, but just remember that Lagrange interpolation can be computed in roughly O of n squared time. In our case, we have four rows. So for each column, there's a unique polynomial of degree at most 3 that matches the values in that column at x equals 0, 1, 2, and 3. This result holds over any field, including finite fields, which is what we'll be using in SNARKs. The important takeaway is that these polynomials are guaranteed to exist and be unique. I've gone ahead and constructed those polynomials for you, and they look like this. A of x equals x cubed plus x squared plus 2. B of x equals 2x cubed plus x plus 1. C of x equals 3x cubed plus x squared plus x plus 3. Take a moment to check this for yourself. If you plug in x equals 0, 1, 2, and 3, you'll see that each polynomial produces exactly the values from our original equations. And here's the punchline. We've condensed 4 separate equations into a single polynomial identity. We can now write just one equation, a of x plus b of x equals c of x. When we evaluate that at x equals 0, 1, 2, and 3, we recover the same 4 equations we started with. So if we were to check the 4 equations, instead of checking 4 separate equations individually, we could check a single polynomial relationship. And that one check captures all 4 equations at once. The amazing part is that this idea isn't limited to just 4 equations. The same approach works no matter how many rows or equations we start with. We could condense 1,000 equations into a single polynomial relationship, or 1,000,000. The thing that would change with adding more equations, though, is that the degree of the polynomials a of x, b of x, and c of x would grow. In our example, we had 4 rows, so the maximum degree of these polynomials was 3. If we had 1,000 rows, the degree of the polynomials could go all the way up to 999. Great. So now let's go back and try a different example, this time using multiplication instead of addition. Suppose I have 4 equations. 1 times 1 equals 1, 3 times 4 equals 12, 13 times 13 equals 169, 37 times 34 equals 1258. We can go through the same process as before. Assign x values to the rows, x equals 0, 1, 2, 3, and construct polynomials, a of x, b of x, and c of x, so that evaluating each polynomial at the x value of that row gives the corresponding value in that row. So a of 0 equals 1, a of 1 equals 3, etc. Doing that, we end up with the polynomials, again using Lagrange interpolation. A of x equals x cubed plus x squared plus 1. B of x equals x cubed plus 2x plus 1. C of x equals 131 x cubed minus 320 x squared plus 200x plus 1. Now you might wonder, does a of x times b of x equal c of x? Well, not exactly. If we multiply the polynomials, we get a of x times b of x equals x cubed plus x squared plus 1 times x cubed plus 2x plus 1, which is a degree 6 polynomial, while c of x is only degree 3, so they're not equal. But here's the key point. If we plug in our interpolation points, x equals 0, 1, 2, and 3, we find that a of x times b of x equals c of x at those 4 points. That makes sense because that's exactly how we constructed or interpolated the polynomials in the first place. And actually, since our only concern is checking that the 4 original equations hold, we don't really care what happens at any other value of x. We just care that this polynomial relationship holds at only those 4 points. Rewriting the equation, we can say a of x times b of x minus c of x equals 0, only at the points 0, 1, 2, and 3. So why does this matter? What have we just done? As we'll see when we dive into how SNARKs are made, it all comes down to checking that a certain polynomial equation, something like a more complex version of a of x times b of x minus c of x equals 0, holds at a specific set of points, similar to x equals 0, 1, 2, 3 in our example. To recap, we've condensed 4 multiplication equations into a single polynomial equation that we want to be true at a predefined set of points. This pointwise check is the key idea that underlies how SNARKs verify computations efficiently. But so far, to check that our polynomial equation holds at the points 0, 1, 2, 3, we've just been plugging in each point, like checking that a of 0 times b of 0 equals c of 0. But that's a little inefficient since we need to do it 4 times. But isn't the whole point of using polynomials so that we can make things more efficient? In the addition example, we could check all 4 equations at once by checking one polynomial identity. So now, can we check all 4 multiplication equations at once with one polynomial identity check as well? As it turns out, we can. Let's define a polynomial to represent the left-hand side of our equation. P of x equals a of x times b of x minus c of x. Now we want to check that p of x equals 0 at x equals 0, 1, 2, and 3. Another way to say this is that p of x has roots at those points. By the factor theorem in algebra, a polynomial has a root at r if and only if x minus r divides it. So if p of x equals 0 at x equals 0, 1, 2, and 3, then the polynomial x minus 0 times x minus 1 times x minus 2 times x minus 3 divides p of x. In other words, p of x divided by x minus 0 times x minus 1 times x minus 2 times x minus 3 will itself be a polynomial. If p of x is not 0 at even one of these points, then dividing by this product will not give a polynomial. Let's give some names to these terms to make them easier to work with. The polynomials x minus 0 times x minus 1 times x minus 2 times x minus 3 in our example is called the vanishing polynomial. You'll often see this written as z sub h of x, and I'll use that notation from now on. Essentially, it's just the product of x minus each of the points where we want to be 0. When p of x is divisible by z sub h of x, you get another polynomial, which is called the quotient polynomial, and is usually denoted q of x. In other words, p of x divided by z sub h of x equals q of x, also often written as p of x equals q of x times z sub h of x. That's saying the same thing. So to recap, what we have done is turn a of x times b of x minus c of x equals 0 check at 4 points x equals 0, 1, 2, 3 into one check of the equation p of x divided by z sub h of x equals q of x, where p of x equals a of x times b of x minus c of x, and z sub h of x equals x minus 0 times x minus 1 times x minus 2 times x minus 3. To complete the example and make this concrete, recall our example polynomials. A of x equals x cubed plus x squared plus 1. B of x equals x cubed plus 2x plus 1. C of x equals 131x cubed minus 320x squared plus 200x plus 1. Then the polynomial representing the left-hand side of the multiplication equation is p of x equals a of x times b of x minus c of x, which equals x to the 6th plus x to the 5th plus 2x to the 4th minus 127x cubed plus 321x squared minus 198x. If we divide p of x by our vanishing polynomial, we get the quotient polynomial q of x, which turns out to be x squared plus 7x plus 33. Feel free to pause here and double check the math. The key takeaway is that we ended up with the proper polynomial q of x, not a fraction that couldn't be simplified. That's exactly what we want. It shows that p of x is divisible by the vanishing polynomial z sub h of x, which is equivalent to saying that the original equation holds at all the points in our set, which are 0, 1, 2, and 3. And here's the important conceptual point. If we can prove that p of x divided by z sub h of x equals q of x, then we have effectively proven that the original 4 equations hold without having to plug in each of the values 0, 1, 2, and 3. Now that we understand this, it's a good time to talk about the Schwartz-Zippel Lemma, which will let us check polynomial identities more efficiently. So we just learned that we can turn the problem of checking a polynomial equation, like a of x times b of x equals c of x, at specific points such as x equals 0, 1, 2, and 3, into a different problem. Instead of checking those points one by one, we check whether p of x divided by z sub h of x is actually a polynomial, which we call q of x. Another way to say it is this. If I hand you p of x, the vanishing polynomial z sub h of x, and a claimed quotient q of x, can you efficiently check that p of x divided by z sub h of x equals q of x? Well, suppose I'm acting as the verifier. One straightforward approach would be to perform polynomial division. Just divide p of x by z sub h of x and see whether that result is exactly q of x. Another equivalent approach is to multiply z sub h of x by q of x and check whether that product matches p of x. Both methods are perfectly correct from a mathematical standpoint. However, they are computationally expensive. For example, let's say I'm the verifier and somebody gives me z sub h of x equals x minus 0 times x minus 1 times x minus 2 times x minus 3, and q of x is x squared plus 7x plus 33, and p of x equals x to the 6th plus x to the 5th plus 2x to the 4th minus 127x cubed plus 321x squared minus 198x. If I want to check whether z sub h of x times q of x equals p of x, I have to expand all that out. That involves multiplying several polynomials together, generating many intermediate terms along the way. Even using standard algebraic expansion, the amount of work grows quickly. And remember what we're trying to build here, SNARKs. The S stands for succinct. That means the verifier's job needs to be extremely fast, ideally taking time that doesn't grow with the size of the computation. Doing full polynomial multiplication or division just doesn't cut it. So this straightforward, naive approach is just too slow for our purposes, and that's exactly why we need a smarter approach. This is where the Schwartz-Zippel Lemma comes in. The core idea is simple. Instead of checking a polynomial identity everywhere, the verifier picks a random point z and checks whether the identity holds at that single point z. If it does, then with high probability, the identity is genuinely correct, not just accidentally true at one value. For example, to check whether p of x equals z sub h of x times q of x, the verifier could expand everything out and compare the full polynomials. That approach gives absolute certainty, but it's slow. Alternatively, the verifier can choose a single random value z and check whether p of z equals z sub h of z times q of z. This is much more efficient from the verifier's perspective. The verifier is given the values of p of z and q of z, so they don't need to compute those themselves, and they independently compute z sub h of z, which can be done efficiently. We'll see how later. Crucially, the verifier never touches the full polynomials. Everything is reduced to scalar field values, so they simply multiply two scalars, z sub h of z and q of z, and check whether the result equals the scalar p of z. I want to delve deeper into one more important point about efficiency. In our running example, we had just 4 rows, 4 equations, and we condensed them into a single polynomial identity, a of x times b of x equals c of x. But this idea doesn't stop at 4 rows. If we had 100 rows, or even 1,000 rows, we could use the exact same method. We would still end up with a single polynomial identity of the same form, a of x times b of x equals c of x. The only difference is that the polynomials would be higher degree. With 4 rows, the polynomials had degree at most 3. With 100 rows, they would have degree at most 99. As a result, the derived polynomials p of x, z sub h of x, and q of x also have higher degree. This means the prover has more work to do, which is expected. The prover's job scales with the size of the computation. What's remarkable, though, is that the verifier work barely changes. The verifier still receives just the scalar values p of z and q of z, computes z sub h of z at a single point, and checks one equality between field elements. From the verifier's perspective, checking 4 equations or checking 1,000 equations almost looks the same. This is the key takeaway. We can dramatically increase the number of equations in the computation while keeping the verifier's work essentially constant. That is exactly what we mean when we say SNARKs are succinct. Okay, now at this point we've traded a slow deterministic polynomial check, p of x equals z sub h of x times q of x, for a fast probabilistic one, p of z equals z sub h of z times q of z. The key question then is how safe that trade-off really is. Well, if this equality holds at a randomly chosen z, we actually can be quite confident that the polynomial identity holds everywhere. In practice, the probability of error is extremely small. So what does quite confident actually mean? How confident are we exactly? Let's see. To answer that, recall that in SNARKs, all arithmetic is done over a finite field. For example, suppose we're working over the field f331. That means all coefficients and input values for our polynomials come from the set 0, 1, 2, all the way to 330. When we pick a random z from this field, there are 331 possible choices. Now let's look at our specific polynomials. Suppose p of x, z sub h of x, and q of x are as before. To analyze this, let's define a new polynomial, d of x, that equals p of x minus z sub h of x times q of x. Notice what d of x represents. If the identity does hold, then p of x minus z sub h of x times q of x equals 0 for all x. So d of x is the zero polynomial. It's 0 everywhere. If the identity does not hold, then d of x is a non-zero polynomial, meaning it is not 0 everywhere. What we want to know is in the second case, when d of x is a non-zero polynomial, what's the probability that a randomly chosen z will make d of z equal 0? Because this is the probability of error. Now recall a key fact about polynomials over a field. A non-zero polynomial of degree d can have at most d roots, points where it evaluates to 0. In our example, p of x has degree 6, and z sub h of x times q of x has degree 4 plus 2, which equals 6. Therefore, if the identity is false, d of x has degree at most 6, so it can only be 0 at up to 6 different values in the field. Those are the only accidental points where p of z equals z sub h of z times q of z might actually hold, even though the identity is false. So if we pick a random z from our field of 331 elements, the probability of hitting one of those points is at most 6 out of 331. 6 bad points out of 331 possible choices. In general, the probability of an unlucky hit is at most d out of the size of the field, where d is the degree of the non-zero polynomial. In our example, 6 divided by 331 is actually relatively large, but in practice, SNARKs use extremely large fields, typically 256 bits or more, so the size of the field is approximately 2 to the power 256. In that case, the probability of randomly picking a z where d of z equals 0 when d of x is not the zero polynomial is minuscule, essentially 0. If a smaller field needs to be used, for example of size 2 to the power 64 or 2 to the power 32, we can pick a few independent random points like z1, z2, etc. to further reduce the chance of error. One subtlety in this is that the argument depends on the degree d. If the prover could arbitrarily choose the degree, they could try to make it very large and increase the chance of accidental success. In a SNARK, however, the protocol ensures that the prover cannot control or inflate the degree of the polynomial, so this kind of attack is prevented. This pattern, many equations collapsing into a small number of polynomial checks at a particular point, is the core idea we'll keep building on in real SNARK constructions. Before we wrap up this video, let's take a small step back and revisit one last idea, polynomial interpolation. So far, when we talked about interpolation, we've been using very simple evaluation points, x equals 0, 1, 2, and 3. I mentioned that using Lagrange interpolation, we can always construct an at most degree n-1 polynomial that fits n points exactly. I also pointed out that the naive version of Lagrange interpolation takes about O of n squared time, where n here refers to the number of rows. That worked perfectly fine for toy examples, but in SNARKs, we're often dealing with thousands, millions, or even more rows. At that scale, constructing polynomials this way would be far too slow. So the natural question is, can we keep the same ideas of interpolation, but choose our evaluation points more cleverly so that everything stays efficient? This is where the fast Fourier transform, or FFT, and roots of unity come in. FFT, more specifically the inverse FFT, lets us perform polynomial interpolation in O of n log n time, which is a huge speedup. For example, if n equals 1,000, then n squared equals 1,000,000, while n log n is only about 7,000. That difference really matters at scale. The catch is that FFT only works efficiently if we pick our evaluation points in a very specific way. Instead of indexing rows as 0, 1, 2, 3, we index rows using special values called roots of unity. Here's a definition. The nth roots of unity are the numbers that satisfy x to the power n equals 1. That's it. Now, a nice property of these values is that you can generate all of them from a single number, the generator, which we usually denote as omega. If you keep multiplying by omega, you cycle through the entire set of the roots of unity. To be clear, the set of the nth roots of unity look like omega to the power 0, omega to the 1, omega to the 2, and so on, up to omega to the power n minus 1. Multiplying by omega just moves you to the next value. This simple cycling behavior is exactly what makes FFT work efficiently. And each one of these values in the set, when raised to the nth power, equals 1. Here's a small example to make it concrete. In the finite field F5, the fourth roots of unity are 1, 2, 4, and 3, where omega is 2. That's because 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 4, and 2 to the power 3 is 8, which mod 5 is 3. And you can check that each of these roots of unity, when raised to the fourth power, equals 1. 1 to the power 4 is 1, 2 to the power 4 mod 5 is 1, 4 to the power 4 mod 5 is 1, and 3 to the power 4 mod 5 is 1. Feel free to check it yourself. So instead of indexing by x equals 0, 1, 2, 3, if we have 4 rows, we index by the fourth roots of unity, omega to the 0, omega to the 1, omega squared, and omega cubed. If instead we were working with n rows, we would instead index by the nth roots of unity, omega to the 0, omega to the 1, omega squared, and so on up to omega to the power n minus 1. And here's the really nice bonus. Remember the vanishing polynomial z sub h of x? If we index by the roots of unity, z sub h of x equals the product from I equals 0 to n minus 1 of x minus omega to the I. Well, it turns out that this product simplifies beautifully to x to the power n minus 1. This is extremely important for efficiency. Earlier, I mentioned that the verifier can compute z sub h of z for a random point z efficiently. That's because if we're using the roots of unity, z sub h of z is just z to the power n minus 1, which can be evaluated really quickly using repeated squaring. That's a huge win. This is exactly the kind of trick that makes SNARKs work. The prover still does the heavy lifting, constructing large polynomials and doing expensive computations, but the verifier only needs to check a few things at a single random point, very efficiently. Thanks to roots of unity and FFTs, we can handle massive computations without slowing down the verifier, which is a big part of what makes SNARKs succinct. That's it for now. Today we talked a lot about polynomials, so let me leave you with a few key takeaways I'd like you to remember. First, we use polynomials because they let us aggregate many equations into a single polynomial equation. We saw how to take a whole set of equations, index each row by values like x equals 0, 1, 2, and 3, and combine everything into one polynomial equation using Lagrange interpolation. Then we explained how, in practice, we don't actually use those evaluation points. Instead, we index by roots of unity, so x equals omega to the 0, omega to the 1, and so on, and use the inverse FFT to do this efficiently. Next, we talked about how we check correctness. Instead of directly checking that a polynomial is 0 at our desired points, we rewrite the condition as p of x equals z sub h of x times q of x, where we check that q of x must be a polynomial. Then, rather than check this equation by multiplying out the polynomials, we check this equation at a single random point z. By the Schwartz-Zippel Lemma, if the equation holds at this random point, we can be very confident that it holds everywhere. We covered a lot today, and I tried to pack everything you need to know about polynomials for zkSNARKs in a single video. If this felt fast, I definitely recommend re-watching it before moving on. Polynomials are going to come up again and again in the upcoming videos. Thanks for watching, and I hope you continue with the series. See you next time.